Hello everyone, this is Sachin Singh. You are watching the Carruthers series. Okay, so let us discuss the new example of this particular Carruthers reference. So this is the new reaction. Okay, so this is our substrate. Cyclohexanone molecule. Okay, this is our substrate, cyclohexanone. This is our reaction condition. This is our intermediate, and this is our electrophilic substrate. Okay, electrophilic substrate. This is our second reaction condition. We can say second reaction condition. And this is our substituted cyclohexanone, that is 2-methyl cyclohexanone. This is our final product. So let us discuss the mechanism of this particular example. So this is the mechanism. So let us discuss the mechanism of this particular substrate. So substrate is basically cyclohexanone. So this cyclohexanone is a symmetrical molecule. Okay, so this is the alpha carbon, first, second, third, 4, 5 and 6 carbon. So this is first and fifth carbon is alpha carbon. So this is also alpha carbon and this is also alpha carbon, and these alpha carbon having hydrogens, two hydrogens like this. This is hydrogen. Okay, so we know that when this carbonyl compound, which is having alpha hydrogens, when treated with a base like lithium diisopropylamide or lithium hexamethyl disilazide, what will happen? Simply acid base reaction takes place. Simply acid base reaction takes place. Okay, simply acid base reaction takes place because these alpha hydrogens are acidic in nature, because when this base abstract proton, there is a formation of anion on this particular carbon, and this anion is stabilized through this particular electron withdrawing group. We know that. Okay, so let us discuss the mechanism of this particular example. Let us discuss this mechanism. Okay, so this is the cyclohexanone molecule. So let us discuss step number 1. So what is the step number 1? Step number 1. So this is the cyclohexanone. So this is the alpha hydrogen. This is also alpha carbon and contains alpha hydrogens. Okay, this is also having alpha hydrogen. So in the presence of LDA, Iain diisopropylamide, lithium diisopropylamide. This is a lithium diisopropylamide. So this lithium diisopropylamide is a non-nucleophilic base. Okay, so it is not at all act as a nucleophile. So it is act as a base, and it will generate the complete inlet. So it will take the proton, alpha proton. So out of two sides, it will abstract proton from the one side, because both sides are symmetrical in nature. So it will take abstract proton from this particular carbon, and there is a formation of anion on this particular carbon, and this. Okay, there is a breaking of this particular sigma bond, and there is a generation of this anion over here. There is a generation of anion over here. I will remove this. There is a generation of anion over here. And that anion will do the conjugation, and there is a formation of unolate anion like this. Okay, after abstracting the proton, there is a formation of anion over here, and this anion will do the conjugation like this, and this bond will break like this, this bond will open up like this, and there is a formation of unolate anion, and lithium will coordinate this particular system like this, and there is a formation of amide. Secondary amide like this. So this is unstable, This is unstable and highly reactive. Okay, this is unstable and highly reactive. Highly reactive. So in this compound treated with a methyl iodide type of substrates, electrophilic substrates, what will happen? Polyalkylation will happen. Polyalkylation will happen. Polyalkylation will happen. So we don't want polyalkylation, we want monoalkylation. What we need to do? This is the big question arises over here. So to avoid polyalkylation, what we need to do? We need to add Lewis acid, that is manganese dihalide or manganese dibromide or manganese dichloride. Okay, when you add, okay, let us take new slide. So this is a highly unstable. If I directly do the reaction by using this particular enolate system, then what will happen? Polyalkylation will happen, and we don't want that. So this is the problem. So how to overcome that particular problem? Simply we need to add manganese dichloride, single manganese dichloride. Okay, so when we add manganese dichloride, what will happen? So this is act as a hard center. This is hard center. This is a hard center. Okay, this is hard center. Metal is electropositive in nature. This is hard center, and this is also hard center. Okay, so this will attack on this particular electrophilic center. This is this particular electropositive element, and this will leave out from the reaction because chloride is a more good leaving group. Okay, because of vacant d orbital. Okay, so there is a formation of this particular manganese enolate anion. Okay, Mn X is equal to Cl, or we can take bromine, or we can take iodine, like this. Okay, so what we did was we simply converted this particular highly reactive enolate into the less reactive enolate. Okay, so this enolate is less highly aggregated in the solution, that is why highly unstable and becomes more reactive. So we need to overcome the reactivity of this particular enolate anion. So what we need to do? Simply we need to convert this. Simply we need to use this particular manganese dichloride. Okay, so after formation of this particular less reactive enolate, that is manganese coordinated enolate, we need to react with the methyl iodide. When we do the reaction of this particular enolate with the methyl iodide, what will happen? Simply this can come back like this, or this. Simply what will happen? Whatever the lone pair which is present on this particular oxygen, it will come back like this, and this will attack on this particular electrophilic center, and this will leave out from the reaction. So minus iodine will leave out from the reaction. So it is electrophilic in nature. So this substrate is electrophilic in nature. You know it very well. Why? It is just because of this iodine is more electronegative group. This will pull electron towards itself. Apply inductive effect over here. This iodine will pull electron towards itself, due to which partial charge will develop on this particular adjacent carbon atom. So this will carry del positive charge, and this will carry del minus charge. When it pull electron towards itself, it will carry del minus charge, and it will carry del positive charge. When it carry del positive charge, at the same time what will happen? This nucleophile will attack on this particular electrophilic centers, and this iodine will leave out with bonding electrons. And there is a formation of this particular substrate. There is a formation of this particular intermediate, because still this is charged species, and charged species are always unstable, hence it is intermediate. Okay, yes, and there is a formation of methyl over here. Okay, so whatever the iodine which is leaved out from the reaction, it will again attack on this particular Mn system, manganese system, and this will this bond will break and this charge will, this bonding electrons will shift on this particular oxygen, and there is a formation of this particular substituted methyl system over here like this. So this is the 2-methyl cyclohexanone. So we got monoalkylated product, monoalkylated product we got. So we have solved the problem, we resolved the problem. So we did the monoalkylation, which is possible in the presence of this particular manganese dihalide system. So this is our main concept in this particular reaction. Okay, so let us discuss the new example of this particular Carruthers reference. Okay, so this is the new example. Okay, new reaction, second reaction. Okay, this is the second reaction. So this is our substrate. So this is methoxymethane. This is our substrate. This is the protecting group of oxygen or carboxylic acid, or this is the protecting group of alcohol. Okay, so this is the protecting group, this is our substrate, this is our reaction condition. So reaction condition, so what they have mentioned? They have mentioned lithium diisopropyl amide in the presence of lithium diisopropyl amide in the presence of tetrahydrofuran, and second electrophilic reagent is benzyl chloride. So again, what we need to do? Again, this is the carbon-carbon bond formation reaction. Again, this is the carbon-carbon bond forming reaction. Okay, carbon-carbon bond forming reaction. And what is the product? So this is our product. This is our final product of this particular example. Okay. So let us discuss the mechanism of this particular reaction. So step number one. What is the step number one? Generation of enolate or formation of enolate. So before that, you need to understand that LDA, again I will repeat this, LDA structure of this LDA is Iain isopropyl, Iain second isopropyl group. Okay, that is why diisopropyl, we call it as a diisopropyl amide minus and a lithium plus. Okay, so this LDA is non-nucleophilic base, and strong base, very strong base. Third one is, it will generate complete enolate formation will take place. It will generate, there are two types of enolate system. One is a partial enolate and another one is a complete enolate. So it will form complete enolate formation will take place. Complete enolate formation, that is 100% enolate formation takes place. 100% enolate formation takes place. Okay, and it is a bulky base. Okay, so it will abstract proton from the lesser hindered region. So let us discuss the mechanism. Step number one is formation of enolate. Step number one is formation of enolate anion. Step number one is formation of enolate anion. I will remove these, please. I will write the substrate. So this is our substrate, C double band O, OMe, and here also C double bond O, Iam, E, Iam. This is the protecting group. Okay, step number one, we are discussing step number one. So when we treat with lithium diisopropyl amide, when we treat this substrate with the lithium diisopropylamide, what will happen? Formation of enolate takes place. How? So this is the alpha carbon, which is acidic in nature. We know it very well because after formation of anion, it can do the conjugation. It can also do the extended conjugation. Okay. So delocalization is there, through which the anion can be stabilized. Okay. Through minus M effect. So this will take the proton from the alpha site. So this is alpha hydrogen, it will abstract the proton, and there is a breaking of this particular carbon hydrogen bond will take place. This will move further, this charge will move further like this, and there is opening of this particular bond takes place like this. So it will abstract proton from this site only because lithium will chelate. Lithium, first of all, what will happen? Lithium will chelate over here. So again, electrophilicity of this particular carbon increases. Again, it will pull electron towards itself, due to which again this is highly electrophilic in nature, so due to which again it will pull electron from this particular site like this, and again this is electrophilic in nature, so again whatever the hydrogen which is directly attached to this particular carbon, again it will carry more electrophilicity, so acidity increases. As the electron withdrawing group increases, acidity of alpha carbon, acidity of alpha hydrogen increases. So it will abstract proton, and there is a formation of enolate anion like this. So I will generate one anion system. So this is the C double bond O-O-M-E. This is the S star. So here formation of enolate takes place like this. O minus O-M-E yam. Okay. So lithium will automatically come over here and coordinate this particular negative charge. So this is enolate. This is enolate. This enolate when we treat with benzyl chloride, okay, benzyl chloride. This enolate when we treat with benzyl chloride, what will happen? Simply nucleophilic substitution reaction will happen. SN2 reaction will happen. So exactly opposite to this particular sigma bond, this is the carbon chlorine bond, this is a sigma bond. Exactly opposite to this particular 180 degree to this particular sigma bond, one sigma star orbital is present over here. So this anion can come back like this, and this will attack on the sigma star orbital of this particular benzyl chloride, and this chlorine will leave out with the bending electrons. You know it very well that this chlorine is pulling electron towards itself, due to which this partial charge is generated over here on this particular carbon. So you can think like this. You can also think like this, or you can think by using molecular orbital theory. Okay. So molecular orbital theory is the most important theory that we need to understand. Okay, so it will attack over here on the electrophilic center or sigma star orbital of this particular benzyl halide. This chlorine will leave out from the reaction because very good leaving group, Cl minus will leave out from the reaction, and there is a formation of this particular substrate over here like this, C double bond O PH. So this is the formation of product. So O-M-E-M, methoxymethyl. So this is our final product. So we will stop here. We will discuss new reaction in the new lecture. Thank you very much for watching the video. Please do like, share, subscribe to my channel, and watch the lectures in incoming days. Thank you very much, and also share to your friends, your colleagues. Thank you very much. I will stop here.